I'm going to talk in this short video about some new calculations that my graduate student John Kummer and I have done on the climate sensitivity. Let me begin by defining what the equilibrium climate sensitivity, also referred to as the ECS, is. It's the amount of warming you get if carbon dioxide is doubled and then the system runs to steady state, and it's one of the most important parameters in the climate change debate. So how do we calculate ECS? Well, one way to do it is to use climate models. You take a climate model, you double the carbon dioxide, and you see how much warming you get. That's pretty simple and straightforward. If you want to use observations, then you have to pick some time period over which the climate is changing and try to infer the sensitivity that way. So you could use, for example, the paleoclimate record and look at ice ages or the climate change between the Eocene and today. Or you could use interannual variations, such as the cycling between El Niños and La Niñas. Or you could use the warming over the last century, in which case you're using the 20th century observational record. Now, the problem with these estimates is that they don't all agree. So climate models, paleoclimate data, and interannual variations all give you a climate sensitivity of about 6 degrees Fahrenheit for doubled carbon dioxide. But the 20th century observational record, on the other hand, only gives you a climate sensitivity of about 4 degrees for doubled carbon dioxide. And it turns out that that's a big difference in the impacts we expect from climate change and how severe the problem is. So how do you calculate climate sensitivity? Well, the first thing you need to know is what's called the forcing, which is the amount of energy that you're trapping by adding stuff to the atmosphere. So we know, for example, that when you add carbon dioxide, you trap heat in the climate system. We also are adding aerosols, which both trap heat and reflect sunlight back. And the sum of all of these things, expressed typically in units of watts per square meter, is the forcing. And then you take how much warming you've gotten in response to that forcing. So you take the 20th century temperature record, and there are lots of estimates of that, which we can have pretty high confidence in. And then based on those two things, you can figure out how much warming you get per unit of forcing, which then means you can translate that into how much warming you get if you doubled carbon dioxide. At this point, it's worth thinking a little bit more about the forcing term of the calculation. It's important to recognize that not all forcers are exactly the same. So some forcing agents, like carbon dioxide, have a very long lifetime, and as a result, they are well mixed in our atmosphere. It doesn't really matter where you go. If you measure atmospheric carbon dioxide, it's going to be about 400 parts per million, give or take. Other forcing agents, on the other hand, have short atmospheric lifetimes, and as a result, they're mainly found near where they are emitted. So aerosols and ozone are the most important in that category, and they're mainly found in the northern hemisphere mid-latitudes, because that's where industrial production mainly occurs, and these are the things that produce those constituents. A recent paper by Drew Shindell in Nature Climate Change showed that models produce more warming per unit of forcing from aerosols and ozone than they do from well-mixed greenhouse gases. Put another way, 1 watt per square meter of aerosol or ozone forcing gives you about 50% more warming than 1 watt per square meter from carbon dioxide. Previous estimates of climate sensitivity based on the 20th century observational record have all assumed that the efficacy of all forcers were equal and equal to 1. And when you do that, you do indeed get a 4 degree Fahrenheit estimate for doubled carbon dioxide climate sensitivity. What John and I did in our paper is we adjusted the forcing to account for a greater efficacy for aerosols and ozone. And when you do that, you end up with a climate sensitivity for the 20th century observational record of about 6 degrees Fahrenheit, in very good agreement with the other estimates. In conclusion, by taking forcing efficacy into account, we are able to resolve the differences between the various estimates of climate sensitivity, and we find that our best estimate of climate sensitivity is about 6 degrees Fahrenheit or 3 degrees Celsius, and that's in excellent agreement with the IPCC's canonical range. We don't see any evidence to support the very low values of climate sensitivity that some climate skeptics have been arguing for.